So, generally, the area of computer vision in early 1960s or 1970s, it used to be called image processing. Image processing, where you detect an edge detection by Canny's method, Sobolev method, some other methods. Then it became segmentation. Actually, you take an image and you do thresholding. What is image thresholding? All the pixels with values above some number, they belong in one image. Those values below that, they belong in another image. See, this thresholding idea proved to be very useful idea. Generally, in an image, suppose this gentleman is there. The pixels corresponding to him versus the background, they are different. So the foundations of computer vision is based upon processing images. I got an image from satellite, but it is very noisy. Some kind of speckle noise or some kind of salt and pepper noise is there. Then I want to take out that.
Nothing, please. I'll just make it slideshow.
Yeah. So, thresholding was there. Then people immediately said, can I detect the edges? Can I detect where an edge is there? You have the background, you have an object here, and the object has some edge. Can I detect the edge? So edge detection became very popular. Then from edge detection, the next level of difficulty, always remember, when you do research, first try to solve simple problem. First solve a simple problem, see what's happening. Gradually make the problem more difficult and slowly solve the more difficult problem. So, the next level of difficulty is, in this room, I have chairs, I have table, I have a TV, and I have a podium. So, given an image, how do I recognize these? Or, when I was a master's student at Louisiana State University, believe me, I don't know how many of you work hard. Our professor gave a data of the Mississippi River and some vegetation, some residential buildings. Our professor said, you got to submit the project. So at that time you used to write programs in Fortran. Possibly you never heard of Fortran. We used to write programs in Fortran. So I started about 8 o'clock and about 2 o'clock in the morning I deleted my code. So I had a hard copy. So I had to type the whole thing all over again. So the problem statement is, we have a bunch of images with a river, with vegetation, with residential buildings and some other objects. So given the image, tell me where the river is, tell me where the residential areas is, tell me where the forest is. This is the problem statement. Even to this day with CNNs, it's a classic problem. Image segmentation or video segmentation. So the foundations of computer vision go back to image processing. Then came image analysis. Can you analyze a given image and extract higher level information? So that's another problem statement. Yeah, that's it. So here is the outline. We already covered the part 1. Then I intend to go into single layer perceptron. And then I intend to go into multi-layer perceptron. from image processing to computer vision. I'll come back to number 2 and number 3 in a while. Remember one thing, there is originality in every one of your acts. Wherever there is the human vision involved, can we replace them by machines, by cameras, by some other sensors? Like, for instance, you take an autonomous vehicle. Cameras are like eyes for an autonomous vehicle. Can anybody tell me, why do you want to go for autonomous vehicles? Why do you want autonomous vehicles?
Less human effort.
It doesn't have human weaknesses. See, generally a machine when you build, unless it malfunctions, it doesn't have any weaknesses. And a machine can replace a human being with a lot more efficiency and accuracy if it is working. So, suppose there is a vehicle in front of you and I want to be able to see it. I want to know where the closest vehicle is. I want to know whether there is a pedestrian crossing. I want to know whether there is a traffic sign. I want to know whether there is a red light or green light. All this information is extracted by the sensors. You have a radar sensor. When I was at IIIT, there was a Swedish company, a company from Sweden, Volvo I believe, if I remember correctly. They first came out the idea of putting a radar in a vehicle to estimate the distance. So, in some sense, from image processing to computer vision, it became the word image processing, you don't hear it nowadays, but it's under the guise of computer vision. Then, how did convolutional neural networks, how did the word deep learning versus shallow learning, that is, I am going ahead of my time, the number of hidden layers used to be 1 or 2. People slowly increased to 3 or 4. And it so turned out, as the number of hidden layers was increasing, the accuracy started becoming higher, better. So deep feed-forward neural networks to deep convolutional neural networks. Then if I have time, I will go into spiking neuron model. And to be honest with you, see, generally, people from different backgrounds sometimes work on similar problems. For instance, John Hopfield in 1982 published a paper, the so-called Hopfield neural network, 1982. 1972 or 1968, Japanese neuroscientist by name Amari had exactly the same idea. So, but you gotta be honest, Hopfield did a lot more than Amari. See, Amari's paper was there, but nobody recognized the significance of the paper. When Hopfield in 1982 announced his, so a lot of activities started. Why I said that is, Jan LeCun was analyzing handwriting to kind of recognize handwriting. That is the problem he started with. And he came out with this idea of convolution. It so turns out that a Japanese neuroscientist by name Fukushima, he had what's called as cognitron. Exact idea in cognitron is that of Jan LeCun. And Fukushima did it 15 years earlier. from image processing to image understanding. That is, see, we human beings take it for granted how the brain works. You navigate, you know, Dr. Fatima is here and all faculty members are here, some students are here. And you navigate your way. You are not just processing an image, you are doing much more. You are able to understand the relationship between objects in the room and you are able to maneuver your way. Suppose I have a robo and I want a robo to go and give a gift to him. Can the robo do it? Maybe in 10 years, maybe the robo can do it. From pattern recognition to object recognition and scene understanding. The next one is one of the very crucial ideas in deep neural networks is the so-called receptive field. So-called receptive field. That kernel you have has something to do with the receptive field. When I take a look at the people in the room, without my knowledge, there is a receptive field associated with the object that I am perceiving it. So the so-called convolution idea is basically motivated by the biological receptive field. So we want to emulate biological vision and image captioning and such tasks. Okay, so those of you who didn't have any background in CNN, here it is. 2D CNNs, same idea in 1D. So when LeCun was doing object recognition, he had an image, right? Then he had what's called as the kernel. Sometimes people call that kernel. They call it mask, they call it a filter. You convolve this, it is initially initialized with some values. You convolve this with this. Then you do some sort of pooling. So you get future maps. So convolution, subsampling or pooling. Sometimes people call it pooling, some people call it subsampling. Then another convolutional layer, subsampling. Then comes fully connected layers. Alright, so can you take me to the others? Hold on, just please sit down. See, even though the mathematical foundations of or the logic of deep neural networks is limited, people still, when you take some ANNs, there is a clear explanation why they are working correctly. But with respect to CNNs, that logical basis is really not there. We have a limited understanding, unlike multi-layer perceptron. The requirement for large amount of training data, you need large amount of data to get good accuracy. Large amount of training time. It takes maybe sometimes a couple of days or more, but gives better, here it is, but gives better than human accuracy. See, you take a computer 2782 into 5238. 2782 multiplied by 5738. Can you give an answer? Computer or a calculator can give it in. But do you mean to say a computer is more better than you? Computer is GIGO. Garbage in, garbage out. Your program is wrong, you get wrong out. Alright. So there are successful applications of convolutional neural networks, such as image captioning. You put a caption to an image, you annotate a bunch of images, you give multi-label indexing, There are large number of applications in science, engineering, management and other areas. We are moving towards powerful robots emulating and exceeding human capabilities. So, I will come back to perceptron in a minute. Will computational models ever emulate biological vision? This is the main question. Even though we have fairly good models in computer vision as well as learning, deep learning. See, deep learning, you have deep belief networks, you have CNNs, you have autoencoders, and maybe now transformers, things like that. The success of deep learning mainly depends upon high performance computing systems. See, if you want to work on a research problem, real-time deep learning, for a given application, can I get my classification in real time? I don't have too much time available to me. I want to get the class label within maybe 10 seconds or within 10 minutes or 5 minutes. So real-time computer vision or real-time deep learning is still a very nascent area. So you have multi-core machines, GPUs and high-speed networking, optical networking systems. Yeah, please. So, see, generally, lot of research papers in deep learning talk about two things. One is, here is a CNN applied to fingerprint recognition. Here is a CNN trained for speech recognition. Here is a CNN trained for handwriting recognition. So 90% of the research in deep learning is towards applications. Yeah, meanwhile, do you have any questions? While he is getting it ready. Yeah. Thank you. Okay. So, you may be wondering, in the title, there is a couple of words, namely multi-dimensional neural networks. So you may have a question, what is multi-dimensional there? See, this word dimension is a kind of loosely used word. Suppose I give you a vector. The number of components of the vector, two-dimensional, three-dimensional, 100-dimensional vector. Use the word dimension there. Suppose I give you a speech signal and I give you an image signal and I give you a video. The word dimension has a different meaning. Speech signal is one dimension, time is the dimension. Image is a two-dimensional and a video is three-dimensional. So, first, lot of research is available on one-dimensional neural networks. In the case of two-dimensional neural networks, the input is images. There are two independent variables. Three-dimensional, like a video, there are three dimensions. When I multidimensional, the theory not only applies to 1D, 2D, 3D, but it applies to arbitrary dimension. Okay, let's get to the actual goal. Our goal in the case of one-dimensional neural networks is to synthesize units which mimic the functions of biological neurons. We want to synthesize units which mimic the functions of biological neurons. That's our goal. Whether we'll be able to achieve ever, we don't know. Alright? Now, here is the main idea. Let's understand the problem properly. The smallest pattern space is two-dimensional, isn't it? A vector at least has two dimensions, and the number of classes cannot be any smaller than. So let us look at the problem. So we have two dimensions, x1 and x2. First question is, we have represented the patterns by two-dimensional vectors. There are two such classes. One is triangles and the other one is circles. And we want to differentiate between them. That is, here is a black box or here is the classifier. You get a pattern, says triangle or it says circle. By just looking at the coordinates, it does something to tell you whether it is a triangle or it is a circle. So in two dimensions, the simplest function that you can think of is a line. The simplest function that you can think of is a line. And all of you agree, the equation for a line is y equals mx plus c. Good. Now, my coordinates are not anymore x and y. My coordinates are x1 and x2. So, x2 equals mx1 plus c. That's our equation. Suppose we write the equation like this. W1 x1 plus W2 x2 equals t. How many of you agree is that the equation of a line? W1 x1 plus W2 x2 equals t. Is that an equation of a line in the x1 x2 plane? So suppose my functional relationship is W1 x1 plus W2 x2 equals t. Let's do a little trick. Keep W2 x2 on the left side, move W1 x1 to the other side. So W2 x2 equals t minus W1 x1. And x2 equals t over W2 minus W1 over W2 into x1. So I expressed x2 in terms of x1 and the intercept. So you quickly realize that the slope is minus W1 over W2 and the intercept is t over W2. So this somewhat different looking equation is actually a line. It's actually a line in the x1, x2 plane. So now comes the question. I give a pattern, and what does it do? It calculates this magic quantity W1 x1 plus W2 x2 minus t. If x1 x2 lie on the line, this will be 0. If they lie above the line, this will be positive. If they lie below the line, this quantity will be negative. So what I did is, here is my patterns, two-dimensional patterns. They are being given to a classifier. What the classifier does is, it calculates this function and applies the signum function, signum, sign. If it is positive, +1. If it is negative, -1. So for all the circles, this will be -1. For all the triangles, it will be +1. So it may look like magic, but what exactly is the classifier doing is taking input patterns, computing this function, giving an output +1 or -1. Just giving an output +1 or -1. So now comes the question. Suppose we initially choose W1 and W2. If we have chosen them, suppose, let's go back to the second diagram. Suppose initially we choose the weights W1 and W2 to correspond to this line. And our goal is to classify triangles and circles correctly. Will this line do the job correctly? No. That is, our initial choice of W1 and W2 is not correct to give a correct classification. Okay? Now, immediately, what we say, that initial choice, if you fix it, then there is no learning, there is no training. If you fix that initial choice, if you are lucky dip, it may be like this, you are done. But if you are unlucky, that initial choice is wrong and you get misclassification. So, what we did is in 2 dimensions. Suppose we go to 3 dimensions. A linear object in 3 dimensions is a plane. So same thing, x1, x2, x3. Y equals signum of w1 x1 plus w2 x2 plus w3 x3 minus. So if your initial choice was proper, things are nice, you get the correct result. Now we want to invent a new word in 4 dimensions. We are moving away from 2 to 3, from 3 to 4. So in 4 dimensions, we want a name for linear object. So we invented a word, hyperplane. So y equals signum of w1 x1 plus w2 x2 plus w3 x3 plus w4 x4 minus 3. So what this fellow Mekula and Pitts, what they did was what we just now discussed. That's what they did. So we have pattern vector with components little x1, little x2, little xn. We have the synaptic weights w1, w2 and so on up to wn. Now here is the question. These w sub i's are initially chosen. As I explained, the artificial neuron, it computes the function summation j equals 1 to n x sub j w sub j minus t. And I will explain why that minus t is not there in the equation. And you take a signum of it and you say whether it belongs to class A or class B. So far, as we explained with the diagram, if you are lucky, that initial choice is good and classification there is no mistake in it. But if you are unfortunate, if the initial choice is wrong, then the classifier gives a wrong result. So McCullough and Pitts proposed this model, I think 1949 or something like that. What they were doing is, they were conceiving of an artificial neuron which does classification by means of a linear function, namely a line, plane or a hyperplane. It's a linear function. So the limitation is, it does not mimic all the functions of biological neuron. To be very specific, there is no training. That is, if your initial choice is wrong, you get a wrong result, there is no training in the model. So one of the crucial ideas is the need for changing the weights. There is a need for changing the weights. So if you look at this diagram, one simple question. Suppose I found one correct line, one correct plane, one correct hyperplane. Is that unique for this problem? The answer is?
We can have multiple parallel lines also available.
Yeah. So, to be honest, there are infinitely many such lines. If we find one of them, you will have infinitely many such lines. And that question was the correct question asked by a Russian by name Vapnik. Among those multiple hyperplanes, is there a hyperplane which is the best one? Yeah, and we'll come back to it if time permits. So there is no training in McCullough-Pitts. So one of the crucial ideas in artificial neural networks is to be able to change the weights when a classification error occurs. When there is error in classification, we should be able to change the weights. So the question is, what is a correct approach to change those weights? That means, is there an organized approach to train the neural network? So, McCullough-Pitts model is the one where the initial choice of weights remains constant. The moment you allow a change in the synaptic weights, it's called as perceptron. Single perceptron. Okay? So, here is the question. So we all agree, because there is a classification error, our choice of weights is wrong and we need to change it. So suppose we change the weights. Suppose there are 100 patterns, 50 belonging to class A, 50 belonging to class B. Suppose the pattern got into error and we change the weights. The first one got correctly classified with the new weights. Suppose we give a new pattern. Suppose it got into an error. We change the weights, but the first one may now become erroneous. The classification may become erroneous. So, we all agree that there is a need to change the weights whenever a classification error occurs. But the main question is, what is an organized approach? So here it is. I take the 100 patterns, I give it to a classifier, keep changing the weights when there is an error. Do it one time. At the end of first attempt or first trial, some are correctly classified, some are wrongly classified. So we got to do it all over again. Because we want 100% accuracy. So, the main question is, we want a training procedure, we want a learning law, which in repeated trials, in finitely many repeated trials, all the patterns are correctly classified. That is, we want 100% accuracy. We will come back to that requirement in a little while. So perceptron, or the word perceptron, I think, was coined by a fellow called Rosenblatt. So we incorporate training by a variation of weights. That is the weight, jth synaptic weight. So we'll go back to this diagram. So we have taken an input pattern, n-dimensional, by means of, classified by means of a hyperplane. Suppose this got into an error. We got to change W1, W2 and so on up to Wn. Because the classification is wrong.
Escape.
Hold on. So the jth weight at time n plus 1 is the jth weight at time n plus a learning rate eta times the input x sub j times target minus actual value. So the target output either could be plus 1 or could be minus 1. O is the actual output. It so turns out that this simple looking learning law converges. That is, in finitely many trials, these synaptic weights, they converge to a synaptic weight vector which will correctly classify them, provided something happens. The condition is linear separability. What is linear separability? If you look at this diagram, the patterns belonging to circles and triangles are separable by a line, 3 dimensions by a plane, higher dimensions by a hyperplane. So, the convergence of weights using the learning law holds true in the case of single perceptron. Suppose the number of classes is not 2 but more than 2. But the assumption is that they are linearly separable. 2 dimensions or higher dimensions, they are linearly separable. So what do? We take the input pattern vector, we put the perceptrons in a single layer. So the idea of layer comes into picture here. Suppose there is neuron 1 and there is neuron 2. We connect the input components lil x1, lil x2, lil xn to the neuron by means of synaptic weights. Like the index is W11 from first component to the first neuron, W21 from the second component to the first neuron, and so on up to n components to the first neuron. It so turns out that this idea of single layer perceptron was very successful if you know that the patterns are linearly separable. So the input pattern space is divided into several regions using hyperplanes. So the condition for convergence is linear separability of patterns. So those of you who are interested, the proof is available book by Simon Heiking. It's not very easy, but it is not too difficult. There is the proof available. Suppose we come to the case where the number of classes is more than 2. Triangles, circles, rectangles and stars. Suppose the triangles are in the first quadrant, circles are in the second quadrant, rectangles are in the third quadrant and stars are in the fourth quadrant. How many hyperplanes, how many lines do you need? Please understand the question. Two are enough. So, naturally, we want to minimize the number of neurons which can do the correct classification. So, one of the problems is, it's a problem in computational geometry. Given a bunch of patterns in some dimensional space, what is the minimum number of hyperplanes required to classify them correctly? And the problem is, to my knowledge, it is not fully solved. So the natural question would be, we are making a very restrictive assumption that the patterns are linearly separable. So a question that comes out is, suppose in 2 dimensions, are there patterns belonging to 2 classes which are not linearly separable? So the answer is yes. Suppose you look at this diagram. I put the circles closer to the origin in all the 4 quadrants. Then symmetrically in all the 4 quadrants. Then I put the triangles after some radius in all the 4 quadrants. So the question is, are those patterns linearly separable? Because no matter what kind of line you choose, there will be a classification error. There will be a classification error. So what do? So our learning law converges provided the patterns are linearly separable. But the problem comes out, non-linear separability. So we make a compromise. We make a compromise. We compromise on the accuracy percentage. Perceptron learning law, if the patterns are linearly separable, in finitely many epochs, you get 100% accuracy. So the next question is, if the training examples are not linearly separable, we do the best we can. So the natural question is, what do we mean by best? So we introduce some error measure in classification. So the error measure is, suppose there is capital D is the set of training examples. TD is the target output for training example. Word is the actual output of linear unit for training example. See, the neuron, by definition, McCulloch's neuron, if we don't have the signum function, then as a function of the input vector, the output is linear in the input vector. I did tell one thing. Here I have assumed the threshold to be 0. Suppose the threshold is non-zero. What I do is I will use the same model, but I will add another input x x of n plus 1, set it equals to 1, and I set up wn plus 1 equals to minus t. The same model will accommodate that more general case. Okay, so if the training examples are not linearly separable, we need a different learning law, namely the delta rule, which converges towards a best fit approximation to the target. We use linear unit. That is, we temporarily assume that the signal function is not there. A linear unit output is summation j equals 1 to m, w sub j and x sub j. So, our problem statement is, we initially choose the synaptic weights and we give the training examples to a linear unit. We check the output. We have an error criterion which is squared error. There is a reason for it, and most of you know that suppose the error on the first T1 minus O1 is plus 5, T2 minus O2 is minus 5. When we just simply add them, you get 0. But there is error in the first training example, there is error in the second training example. So it so turns out that we run into an optimization problem. What is the optimization problem? Given the training examples, how should we choose the synaptic weight so that the error goes down? So initially we set them, so here is the diagram which explains the procedure. We have here indexed by W0 and W1. We have initially chosen some weights W0 and W1. We have some error. Then we need to change the weights so that the error goes down. We come to a new point. We calculate the error again. And if it is sufficiently small, we stop. Otherwise, we change the weights again. We keep doing this until the error becomes as small as desired. So, the problem is a optimization problem. And you all mostly know that when we have a function of multiple variables and we want to know the direction in which the function increases, we calculate the gradient. It so turns out that the negative of the gradient gives the direction in which the function decreases fastest. So, it's a simple exercise. Suppose error with weights W1 and W2 is half TD minus OD whole square. OD, because linear unit, is W1 x1D plus W2 x2D. When you differentiate it with respect to W1 and W2, 2 get cancelled, TD minus OD remains, times minus x1D or x2D. Whether you want a partial derivative with respect to W1 or W2. So, we know that the direction in which the function increases fastest is the direction of the gradient. But we don't want to increase the error, we want to minimize the error. So, gradient you can easily calculate that it is this quantity. Now the question is, we want to take the synaptic weight vector and change it in the direction of negative of gradient. So we have minus eta, which is the learning rate, times the gradient of the error function. And it is very easy to see that it is summation d belonging to capital D, Td minus OD times minus x sub I. So the change in the ith component is eta, summation d belonging to capital D, Td minus OD times x sub I. Such a learning algorithm is called standard gradient descent. So, if you understand this, you pretty much understand deep learning, or you pretty much understand shallow learning at least. You start with some initial weight vector. You have some error measure. You calculate the gradient of the error function. Move in the direction of negative of gradient. You come to a new point. Then you calculate the error with new weights for all the training pattern. Underline the word all the training patterns. Then you get some other error value. You keep doing this until the error becomes as small as desired. And this kind of learning law, where at every time you change the weights, you are using all the training patterns, that's called standard gradient. But it is computationally very expensive. Every time you change the weights, you have to use all the training patterns. So people have spent a lot of time working on this problem, and they came out with stochastic approximation to gradient descent. Stochastic approximation or incremental gradient. Stochastic gradient or incremental gradient. The only difference, if you look at the equation, this quantity summation d that is taken out. So W sub I of n plus 1 is W sub I of n plus eta Td minus OD times x sub I. It is computationally very attractive. It so turns out that sometimes people rediscover the ideas available in some other area. Like in adaptive filtering, there is a rule called withdraw half rule. Withdraw and half. And this is a LMS rule in adaptive filtering. So now came a very nice question. The question was, can we build computers out of neurons? That is, can we build logic gates out of neurons? So in the simplest formulation, we have 0, 1 as the inputs. 0 or 1. 2 dimensions, 2 input gates. For instance, we want to realize, let us say, OR gate. Pretend that the output minus 1 corresponds to 0 and 1 corresponds to 1. So 0, 0, the output is minus 1. 0, 1, the output is 1, OR gate. 1, 0, the output is 1. 1, 1, the output is 1. You draw a line from 0.5, 0 to 0.5, it will do the correct classification. So the patterns are linearly separable. Now let's go to AND gate, exactly the opposite. or if it's not exactly opposite. 0, 0 output is 0 or minus 1. 0, 1 output is 0. 1, 0 output is 0. 1, 1 the output is 1. So the patterns are still linearly separable. So there was a fellow called Minsky. He asked a question. Can we realize exclusive OR gate? So 0, 0, the output is 0. 0, 1, the output is 1. 1, 0, the output is 1. 1, 1, the output is? So even though we have the logic gates for AND and OR, we cannot classify them by a linear neuron, or we cannot classify them as perceptron. So this was the question being handled, and a lot of funding was stopped for research on neural networks. So there was a fellow at Harvard who was doing thesis in non-engineering department. He said, can I come up with a neural network which will classify non-linearly separable patterns? They are not linearly separable, they are non-linearly separable. So he needed two things. One is the idea of layer, the idea of number of layers should be relaxed. The second one is the kind of activation function, that you choose have to be changed. So the two new ideas he brought in. See, the gradient rule requires you that the function is differentiable. What I didn't say earlier is, even though I assumed a linear neuron, if it works for linear neuron, in the single perceptron case, it works for multiple, for nonlinear activation functions. So first thing he did was, he wanted a way of coming up with a activation function which is differentiable and it gives the same output for the patterns. So if you look at the function 1 over 1 plus e power minus net, this function was called logistic function or logistic map. Suppose the net is minus infinity, then this output will be 0. At exactly 0, the output is half. At plus infinity, the output is 1. So he called that as sigmoid. Sigmoidal neuron or sigmoidal unit. This sigmoidal unit, when you differentiate it, it will be d by dy of sigma of y times 1 minus sigma of y. It's very easy to do this.
So we are running out of time.
Just another 5 minutes. So, the main idea here is relax the number of layers from 1 to more than 1. The second assumption is, or the second idea is, to have an activation function which mimics the signum function, but it is differentiable. So, if you look at this problem, in the output layer, remember, in the gradient rule, you need the desired output. If you look at this architecture, only in the output layer, you know the desired output. The second thing is, because there are multiple neurons in the output layer, the error function previously had only one neuron, but now there are multiple neurons, and this function is no more a convex function. That is, if you look at the diagram, the error function has a single local minima, which is also the global minima. But when the number of neurons increases, the error function is no more, it will not convex, it will have multiple local minimas. So the gradient descent algorithm can get stuck in local minima. The main difference compared to single layer perceptron, the desired output at any unit in the output layer is known, but the desired output at a unit in the hidden layer is not known. That's where, using chain rule, Verbose, the PhD student at Harvard, he came out with the back propagation algorithm. The error is propagated backwards from the output layer to the hidden layer and input layer, and the synaptic weights are updated. The process repeats till the desired accuracy is obtained. Okay, so multi-layer perceptron, formerly Harnick, Stinchcombe and White, even non-linearly separable patterns can be classified using a multi-layer perceptron. So if you look at this diagram, as I said at the beginning, what's called universal function approximation. Inputs are x1, x2, xn. Outputs are y1, y2, yn. Each of them is a function of input. Any arbitrary function can be approximated by a multi-layer perceptron. So the patterns which are not linearly separable in a lower dimensional space can be made linearly separable in higher dimensional space. So as I said, multi-layer perceptron was very successful in many applications. One of the main ideas was, how many hidden layers should be there? How many neurons should be there in the hidden layer? People started experimenting. There are what are called deep feed-forward neural networks. As I said, multi-layer perceptron is a feed-forward network. There is no feedback from the output layer to the hidden layer or to the input layer. So, deep feed-forward neural networks were providing fairly good accuracy. So, I think I'll stop here.
Thank you so much, sir. On behalf of Department of Computer Science and Information Technology and ATAL program, I, Nusrat Fatima, research scholar from Department of CS&IT, thank Professor Murthy sir for giving us a wonderful lecture on the foundations of deep learning as well as the computer vision. Thank you so much, sir. Thank you all the participants for being seated and having a wonderful learning over here. Thank you so much. Yes, we can have a photo with sir.
If you like, you can come over